So now, let's go to seismic design philosophy. Generally, we want buildings to withstand earthquake, and we want the buildings to not fail under earthquake. Or we want to design buildings that if they're going to fail, the building is wise enough and smart enough to give specific time to the occupants to leave the building, either from using the stairs or using the emergency stairs or jumping out of the window. As long as the residents of the buildings are safe outside in an area which the building doesn't harm them, the building can even collapse as well. We don't want to reach to that point, but as long as we have saved the life and no one has lost their life, that is the philosophy that we are following. But generally, we want to build buildings and design buildings that whatever earthquake happens, nothing happens to the building. But as you know, as I know, as everyone knows, that really depends on how much budget you have, how much technology you have, and stuff like that. We cannot build all of our residential buildings as nuclear facilities. Definitely nuclear facilities can withstand very strong earthquakes, but they're appropriately very expensive and very hard to design. So a client of a residential building or even a client of a hospital will not accept that range of damage. So we as designers follow some philosophies to make sure that the damage caused to the building is controlled and limited to the limit that we want it and is acceptable for our client as well. So the main concept of seismic design can be divided into 3 bits: energy dissipation, ductility, and capacity design. As long as we follow these 3 rules in our design of the structure, for a high chance our structure will be earthquake resistant in a way that if an earthquake happens and we have predicted that shaking of the earthquake, we know how our building will perform against it. So either we know that the building will have no damage, or we know that the building will have, for example, life safety damage, so some cracks and stuff, but residents of it will be safe, or it will have some extensive damage, but it won't collapse in a way that it will trap the residents in it or it will crush them. So the residents have enough time to escape from the building. Now let's concentrate on energy dissipation. Let's look at 2 cases: elastic response of the material and inelastic response of the material. We said in earthquake engineering, we consider the inelastic response of the material, so the plasticity. One directional force is applied, and as you can see, the force displacement graph, which as I mentioned, this can be converted to moment, rotation, or even stress, strain. As you can see, for an elastic material, it just goes from A to B, and when I release the loading in point C, which there is no force in it, it goes back to 0. Now look at the inelastic response. I have the column at state A, I apply force, it goes all the way to yielding point, it has some inelastic, some plastic behavior, and then I release the force. Because it has entered the inelasticity, it will have some permanent deformation. You might say that, okay, seems like case A, B, C of the elastic was better because after the force is released, my structure is back to its normal. But to be honest, this is what we are always looking for: elastic, perfectly plastic situation. And why is that? Because I always want my building to start dancing under the earthquake loading that is applied. Why start dancing? Because that dancing and that shaking with the rhythm of the earthquake, we release energy, we release energy, we release energy. And that release of energy is called dissipated energy. Whenever a structure dissipates energy, it means that it will not reach to its ultimate capacity and it will not fail. Whenever a structure is not capable of dissipating energy, it means that it will have sudden failures. Remember that occupant, which we have to give it enough time to leave the building. If my building is not dancing, it means that it's resisting. So my occupant doesn't even understand that there is an earthquake, and suddenly it collapses. That is what I don't want to happen. I want my building to start waking up, to start shaking with the earthquake, and then at that time, the residents will be informed that, okay, the building is shaking, something is happening, so they can reach out of the building. Meanwhile, the earthquake is striking my building is dancing with it, and it's dissipating energy. That dissipation of energy will release the forces on the building with having some performance of permanent deformation. And although that deformation will be permanent, but it will prevent the building from a sudden failure, collapse. So energy dissipation is very important, and we reach to that energy dissipation by allowing our material to move from linear behavior to non-linear behavior. Let's see the same case under an actual earthquake. So earthquake loading, acceleration versus time. So my building is not getting pushed only in one direction, it's now getting pushed and pulled and pushed and pulled. If it's an elastic behavior, it goes O to B and then back to O and then to the next point. As you can see, it goes like this. But when it's an inelastic behavior, it goes O to A and D and then G, and then as you can see, it makes a kind of a cycle and a cycle and a cycle and a cycle. This cycle and cycle will dissipate energy. That dissipate of energy will prevent the structure from a sudden failure. Sudden failure here, sudden failure here. You see, fracture can happen. But this dancing prevents that fracture to happen. So the building will go under permanent deformation, but it will save its residents. So I want energy dissipation, and that energy dissipation is given to me by inelastic response of my material. When I have elastic material like glass, that suddenly there is no deformation, no suddenly collapse, that is something bad in earthquake engineering. I want something to start dancing with me, so remember this. Another concept after energy dissipation is ductility. Generally, our material are either very brittle or they are ductile material with different degrees. So a brittle material, it reaches to a point and a sudden collapse. A brittle material like this high ductile reinforced concrete will reach to a point of yield, and then it starts deforming and deforming and deforming. This deformation will be permanent, but it will prevent from sudden collapse. Again, similar to energy dissipation, ductility will help me prevent a sudden fracture, a sudden collapse, which is like the worst situation in any earthquake failure. So, ductility is the ability of the structure to undergo large deformation. Yes, strain is change of length over initial length. So the higher the strength is, it will have larger deformation or plastic deformation as it has entered the plasticity or inelasticity without failure or ability of a structure component to deform beyond this elastic limit. So structure deforms before collapse without a substantial loss of strength. As you can see, the strength is still the same, while a brittle material like glass, it reaches to that strength and then suddenly zoop all the way to zero. And whatever material is ductile, as you can see, the area underneath the curve, which represented the dissipation of energy, is high as well. So significant energy dissipation for ductile material, while brittle material, exactly again like glass, they have very limited energy dissipation. In earthquake engineering, ductility is how well a building will endure large lateral displacement, meaning earthquake load, imposed by the ground shaking. So ductility factor is an indicator of the ductility of the structure, and it's simply if it's in terms of deformation, it's the deformation at failure or ultimate, yeah, so the last point of the curve of stress strain or force displacement to the yield deformation. So imagine this is the yield deformation and this is the ultimate deformation, so the ratio of this guy over this guy. Now consider this structure as a ductile or ductile beam or ductile column, and consider this structure as a non-ductile or a non-ductile beam or non-ductile column. So a ductile behavior will be something similar to this. This is the same curve, force displacement, force displacement. Then look at this. The ultimate point and the yield point are very close, so this relationship, this ratio will be very small, but in this case, the ductile, this will be a big relationship and the ductility factor will be higher. Now, if the curve is moment rotation, it doesn't really matter. Is the rotation at failure to yield rotation, or if it's based on curvature, it will be moment curvature. So curvature at failure to yield curvature. That will be the ductility factor, or as we show it with mu. Now, we combine that dissipate energy and ductility behavior together, and we kind of give a discount to ourselves. We say that if my building is capable of dissipating energy, and because of that means that I have a very ductile behavior of structural components like beams and columns, I can reduce the level of my seismic action. We will see this when we go into the seismic design based on Eurocode 8. Clearly you will see how much this discount and how much this reduction of level of seismic action works. But for now, remember that the behavior factor combines this dissipation of energy and ductile behavior. There are two methods that we come up with the behavior factor or Q. One is equal displacement rule, which is mainly for flexible and tall structures. One is equal energy rule, which we usually use it for low to mid period structures or stiff and short structures. So the equal energy rule for the White House and the equal displacement rule for Burj Khalifa, let's say. Again, when I talk about Burj Khalifa, we know that its period is 11 seconds, but you can consider it as a tall building with 4 seconds, something like that, as well as the short building, the White House, let's call it, a period of, let's say, 0.4 seconds, 0.5 seconds, so the beginning of the response spectrum and all the way to the end of the response spectrum. So flexible tall buildings and stiff and short buildings. Now, what does the equal displacement rule says? It says, okay, if your behavior is elastic like this, yeah, so this is the elastic behavior. If you want to give a bit of discount, so you reduce the level of your seismic action. So the force, instead of being VE, let's say you have to design it for this, you can come to VD, let's say the design value for your structure, and as you can see, it's kind of half. So you'll when you have less force, means your cross sections will be smaller. When you have smaller cross sections, means you will use less material, concrete, steel, timber, any of those. And then when you have less material, means you have to order less tonnage of material. And then if you order less tonnage of material, your building will be built faster. Fast and less material will cause low costs, and your client will be much happier. So the code allows you, and the same concept, the philosophy of seismic design allows you, that instead of going for the ultimate load of elastic, we think that our building behaves inelastically. We have studied it, that it has some non-linearity, and because of that I can reduce the seismic force a little bit. Now for tall buildings, we follow the equal displacement rule. As you can see at this point, both of them have the same displacement. Yeah, at this point, this is the inelastic behavior, that I assume my building will have, this is what the code initially assumed, the elastic behavior. Now look at the equal energy rule. It doesn't have the same displacement. It says, okay, this is the initial behavior. My inelastic behavior will have something a little bit higher in terms of ultimate displacement. Instead of being stopping here, it will move on. But then the area underneath the curve will be equal. The area underneath the curve was the energy dissipation. So I will have a new structure which acts inelastically, but the dissipation of energy is equal to the same dissipation of energy when I had the elastic behavior. So the area underneath this curve, this triangle, is equal to this shape that I have here. So this is the equal energy rule. The other one, equal displacement, they have the same equal displacements at the end. Now this rule is applied for tall and flexible structures. In this case, the behavior factor is equal to the ductility factor directly. For stiff to short structures, low to medium period structures, the ductility is related to the behavior factor is related to 2 times the ductility minus 1 under the square root. Let's focus and let's zoom on this equal energy rule for stiff and short structures, which is this formulation: the force of elastic over the force of inelastic. The force of elastic, this is the ideal assumed elastic behavior, the initial assumed behavior. This is the intended inelastic behavior. This is what I want to consider my building after considering that it has some dissipation of energy and the material, I allow them to have inelastic or plastic behavior. So if I have this ratio, I will end up with this formulation. And then, as you remember, the ductility factor was the ratio of ultimate deformation at failure to the yield deformation, or if it was rotation or curvature, the ultimate over yield. Always remember this, the ultimate over yield is the ductility factor. The smaller the ductility, these two will be closer to each other. The more ductility, the more ductile, the more energy dissipative material you will have. This ultimate one will be further from your yield point, so it will be a bigger value. The behavior factor considers this in, and lets that come in. Equal energy rule for stiff and short structures with low periods. Equal displacement rule for high period buildings, flexible and tall buildings, Burj Khalifa as well as the White House. We will see how and when we use this behavior factor as well as ductility, although you already know it. So if I draw the behavior factor versus period of the structure, such a graph will be resulted that when the period of the structure is 0, the behavior factor is 1. This is for non-ductile buildings. Now, as we carry on and the structural period increases and increases, we go from a short and stiff structure to tall and flexible structure. Short and stiff to tall and flexible. The more flexible your building is, it takes more time to get back to its initial position, so it has a higher period. So let's say the boundary between these stiff structures and flexible structures, we call it the T corner or TC. So this was the formulation for it. Equal energy rule, as we just discussed, and the equal displacement rule, as we just discussed. And again, ductility factor. So remember how the behavior factor is related to the ductility factor. We have it for high period structures and we have it for low period structures. And it just follows this simple concept of having similar displacement or having similar equal energy. Now, we discussed about energy dissipation, we discussed about ductility and how these two are combined together to have a factor representing them called the behavior factor. Now let's talk about the capacity design. So imagine a chain. If I pull it, at a point, one of these links of my chain will start breaking. Do you all accept that that link which the failure starts at will be the weakest link? Yeah, for sure. Now, we can assume our building, all of its components, from slabs, columns, beams, joists, girders, connections between the columns themselves, between the beams and the columns, connection between the slab and the joint, footing, how the columns are connected to the footing, the foundation, all of these as different links of a chain. Capacity design allows us, designers, us structural engineers, to design our building in a way that that weakest link is in our control. So I will tell the structure, or will address the structure in this way, that if there is going to be a failure, I will decide which of the components of my building will fail first. Now, if I know that weakest link, and I have decided what that weakest link will be, for example, in this case, we have selected beam, and if I make that beam, I put so much effort in designing it, I will put so much effort in its material, and I'll make sure that it's as ductile as possible, meaning that it will dissipate energy as much as possible, and it will be the failure will be shifted very far away, and I'll make sure that all of the other components are definitely stronger than that element. Then I have moved my failure, first of all, to the place that I want to fail, so it causes less damage to all of the other components, as well as I have made sure that all of the other components are stronger, and I can follow the normal, elastic, easy way of designing. So I will spend so much resource, time, money, and material on one weakest link that I have decided what it will be, and I'll make sure that that is the best element possible. Then I'll make sure that the other components are for sure stronger, so they don't fail before my weakest link, and I can design them with a normal situation, any material that I want, and just making sure that its capacity is higher. So let's look at another scenario. So in a normal situation, imagine this is my weakest link. I'll make sure that this weakest link is so ductile that it takes so much long time to fail. On the other side, I'm very happy with all of the other links, like my columns, my connections, and everything else, that they are stronger than my weakest link. So whenever this guy is failing, first of all, the failure is shifted so far because it's a very ductile material and it dissipates energy, so it's very low chance that it will fail. And then I'll make sure that when this fails, before failing, none of the other components, which are very important and more essential to my building's integrity, not to fail before this. If this concept follows, this will never ever happen. Look at this building. You can clearly see that the beams and the slabs are strong. They stayed in their position and they look like pancakes on top of each other, while the columns were designed very weak. Now imagine the other way around. If I have designed the columns very strong, but the beams weaker than my columns, but in a way that those beams were strong enough to dissipate energy and they were ductile enough to dissipate energy, I would give the residents of this building more time that, okay, the beams are starting to dance, the columns are still strong and nothing has happened to them. The worst case scenario, one of the beams in one of the floors will fail. But instead, none of the columns have failed, so all the residents had enough time to get out of the building or jump out of the window. So this would have not happened. So the seismic inertia force are transmitted from the floor to the beams, then to the columns, as always. The failure of the column would affect the stability of the entire building. So columns are one of the most important parts of any building. Imagine if the bottom columns of your building fails, then definitely the whole entire building will fail. Hence, it's best to make beams as weak ductile links than columns, for sure. This design method is called as strong column, weak beam concept, or the same capacity design or ductile chain design that we always follow. This is from earthquake of 2005 Kashmir, very strong earthquake, 7.6 moment magnitude. Unfortunately, 87,000 deaths, 75,000 injured, and 2.8 million people were forced to displace because their houses were completely destroyed. If you look at this scene, it's very, very similar to what we saw in the 2020's Izmir earthquake as well. Exactly the same concept, and unfortunately our designers didn't know how to follow this capacity design. Generally, we tend, in any design that we have seen, we tend to design the columns with much concentration and the best design possible. So the slab and the column and the beams. But when it reaches to the columns, we just use a simple table and we just make sure that it stands, while we have to spend more time on the column instead of the beam. Now, the capacity design, the concept of capacity design from the philosophy of seismic design tells us that, okay, make sure that your beams are ductile enough, design them in a way that they're ductile. Now, perfect, you have a very ductile beam. Now make sure that every single other component of your building, from the connections to the columns to the foundation, are stronger than that beam, so they fail later. But I'll give you a discount. You can design those elements as an elastic one, so an easier design. But at least one of the components of your structure, which in this case will be a beam, should be properly designed as an inelastic element. Let's see some failures which not having a strong column weak beam or having a weak column strong beam has caused. This is the earthquake of 2017 Mexico. Again, a very strong earthquake, 7.1 moment magnitude. Unfortunately, 370 people lost their lives and 6,000 people were injured. If we look at the Mercalli intensity, it was about 8, so it was a severe earthquake. Just concentrating on this building on the right side, you can see definitely the failure starts here. So the column fails, the bottom columns fail, the entire building gives up. Same thing happens on the left as well. The building seems okay, suddenly something happens on the right side, and trust me, definitely it's again a weak column at the bottom which causes the entire building to come again all the way together like a pancake failure. Now, if one of the beams only on the third floor failed, this wouldn't have happened. Only that floor on that bit of the slab would have failed. But the integrity of the building will be kept and residents could have run out.